Welcome to Digital Learning, Department of Collegiate Education. I am Dr. Latha Devi Puli, Assistant Professor, Department of Mathematics. In this video, we discuss about integral calculus of first semester BSc Mathematics. In this session, we discuss about Leibniz's rule which deals with differentiation of a function involving integral sign. The objective of this session is to learn the Leibniz's rule and verify it to some of the functions involving the integral, and by the end of this session, the student will be in a position to verify Leibniz's rule of differentiation under integral sign. The prerequisites are: to do the problems on Leibniz's rule, the student should be familiar with integration and partial differentiation. Now, let us see what is Leibniz's rule. This is session 39, Integral Calculus. Now, in this session, we are going to discuss about differentiation under integral sign, which is given by the mathematician Leibniz. Now, here I am going to consider a function integral of involving the integral, that is integral of a of alpha to b of alpha f of x comma alpha into dx. Here we are doing integration of this function with respect to x, and the limits are from a of alpha to b of alpha, where alpha is the parameter. Parameter is nothing but the variable. So here x is a variable and alpha is also a variable, which we call it as parameter. But here we are doing the integration with respect to x. After evaluating the integration with respect to x, we will be applying the limits which are in terms of alpha, so that the final answer will be a function of alpha. So for our convenience sake, let us choose that as phi of alpha. So the resultant answer, whatever we will be getting after evaluating this integral, let it be phi of alpha, that is equal to integral of a of alpha to b of alpha f of x comma alpha into dx. Here alpha is known as parameter. Once again I am saying alpha is also a variable here. Now, to find the differentiation of this phi of alpha, we have to find the differentiation of this function which involves the integral, which we can't do directly. The differentiation of phi of alpha with respect to alpha we have to do, but here the integration is with respect to x. So we can't do the differentiation under the integral sign directly. For example, if we are doing the differentiation with respect to x, then differentiation and integration will get cancelled and we will have our original f of x comma alpha. But here the integration is with respect to x, but we are doing differentiation with respect to alpha. So that's why the integration will not get cancelled here. So for this, to evaluate this type of problems, Leibniz has given a formula which is known as Leibniz rule of differentiation under integral sign. The rule is like this, as follows. Here the first theorem is Leibniz rule when the limits of integration are the functions of the parameter alpha. So here the limits are in terms of alpha. Then the Leibniz rule is given by, if phi of alpha is equal to integral of a of alpha to b of alpha f of x comma alpha into dx, where a and b are functions of alpha, then d phi by d alpha means the differentiation of this phi with respect to alpha is given by integral of a of alpha to b of alpha dou by dou alpha of, that is the partial differentiation of this function f of x comma alpha into dx, plus d by d alpha of the upper limit of the integral. The upper limit of the integral is b of alpha. So b of alpha into f of this x will be replaced with b of alpha comma alpha minus d by d alpha of the lower limit of the integral, which is nothing but a of alpha into f of in x comma alpha, x is replaced with a of alpha comma alpha. This is known as Leibniz rule of differentiation under integral sign when the limits of the integration are variables which are in terms of alpha. So d phi by d alpha is equal to integral of a of alpha to b of alpha dou by dou alpha of f of x comma alpha into dx plus d by d alpha of the upper limit of the integration b of alpha into f of x is replaced with the upper limit comma alpha minus d by d alpha of the lower limit of the integration into f of x is replaced with the lower limit a of alpha comma alpha. This is the Leibniz rule when the limits of the integration are the parameters. Now the second one is if the limits of the integration are constants, those are not in terms of alpha, then what it happens? That is, if a of alpha is a constant and b of alpha is a constant in this formula, then what it happens in this formula, d by d alpha of this will become a constant. So d by d alpha constant of a constant is 0. So that this entire term will become 0 minus d by d alpha of a of alpha. Here we are saying that alpha a and b, the limits of integration are constants. So a of alpha is a constant. So d by d alpha of this term will become 0. So 0 into this complete term will become 0. So in this formula, the second term and third term becomes 0. So that the above formula becomes d phi by d alpha is equal to integral of a to b dou by dou alpha of f of x comma alpha into dx. This is a Leibniz formula whenever the limits of the integration are constants. Now let us do the problems based on the Leibniz rule. The first problem is verify Leibniz's rule of differentiation under the integral sign for integral of 0 to pi by 2 1 divided by alpha into 1 plus cos x, where alpha is the parameter. Alpha is the parameter means alpha is also a variable here. So here we have to evaluate, we have to verify Leibniz rule for this integrand. That means for this integral of 0 to pi by 2 1 by alpha into 1 plus cos x into dx. So you look at this integral. This integral is a function of x. That means we are doing integration with respect to x and applying the limits in terms of 0 to pi by 2. So after applying the limits, we will be getting the final answer in terms of alpha, because 1 by alpha we are having an integration we are doing with respect to x. That's why I will be taking, since the final answer is in terms of alpha, I am taking let phi of alpha is equal to integral of 0 to pi by 2 1 divided by alpha into 1 plus cos x into dx. Since the limits of integration are constants here, by Leibniz rule, we have d phi by d alpha is equal to integral of a to b dou by dou alpha of the function, means f of x comma alpha into dx. Now, what is f of x comma alpha here? Here f of x comma alpha is 1 by alpha into 1 plus cos x. Now, the problem is given as verify Leibniz rule. So, this is the Leibniz rule. We have to verify that. Means we have to prove that LHS is equal to RHS. So, for that sake, first let us find what is LHS value. LHS is nothing but d phi by d alpha. That is equal to d by d alpha of phi. But here phi is the integral function. That's why first let us evaluate this integral which I have done here. So to find phi of alpha, given phi of alpha is equal to integral of 0 to pi by 2 1 divided by alpha into 1 plus cos x into dx. That is equal to integral of 0 to pi by 2, and we know that as we discussed in the previous sessions, to evaluate this integral, we will be applying multiple and submultiple angle formulae. We know that 1 plus cos x can be written as 2 cos squared of x by 2. So that 1 by cos squared will become secant squared of x by 2. So this 1 plus cos x can be written as 2 cos squared of x by 2. So that this will become 1 by alpha is constant because we are doing integration with respect to x. So 1 by alpha into integral of 0 to pi by 2. This 1 by 2 I written at the beginning, and we know that 1 by cos squared is nothing but secant squared of x by 2 into dx. And we know that integral of secant squared theta is tan theta, and the coefficient of x is 1 by 2 here, which comes in the denominator after evaluating the integral. That's why this will become, that is equal to 1 by alpha into 1 by 2 is constant, bring it out. Integral of secant squared of x by 2 is tan of x by 2. Coefficient of x is 1 by 2. So whole divided by 1 by 2 it will become. Since we evaluated the integral, now we have to apply the limits 0 to pi by 2. So I written the limits on the right side, 0 to pi by 2. Now let us apply the limits for this. So that 1 by alpha is constant, and here 1 by 2 and 1 by 2 will get cancelled. 1 by alpha is constant, I written outside, into tan of, apply the upper limit, that is pi by 2 by 2, which is nothing but pi by 4 minus tan 0. So tan pi by 4 minus tan 0. But we know that tan pi by 4 is 1. So that is equal to 1 by alpha into tan, in place of tan pi by 4 I written 1 minus tan 0 is nothing but 0, that is equal to 1 by alpha. Therefore, phi of alpha is equal to 1 by alpha, which we can write it as phi. So phi is equal to 1 by alpha. That is, here actually our function phi is having integral sign. So I evaluated the integral till now. So after evaluating the integral, we got phi of alpha as 1 by alpha. Substitute that phi value in LHS. So that d by d alpha of phi is 1 by alpha. So differentiation of 1 by alpha is minus 1 by alpha squared. That is what our LHS is. Now let us find what is RHS value. Now RHS is, in RHS of the Leibniz formula is integral of a to b dou by dou alpha of f of x comma alpha into dx. So here RHS will become integral of a to b dou by dou alpha of f of x comma alpha into dx, where f of x comma alpha is 1 by alpha into 1 plus cos x into dx. So integral of 0 to pi by 2 constant limits dou by dou alpha of 1 by alpha into 1 plus cos x into dx. Dou by dou alpha of it is, that is, first we have to do the partial differentiation of this function with respect to alpha, and as we know, differentiation of 1 by alpha is minus 1 by alpha squared into 1 by 1 plus cos x into dx. But we can write 1 by 1 plus cos x as 1 divided by 2 cos squared of x by 2, that is equal to 1 by 2 into secant squared. 1 by cos squared can be written as secant squared of x by 2. So in place of this 1 by 1 plus cos x, I written secant squared of x by 2 into dx. This is integral of 0 to pi by 2, and the integration is with respect to x. So minus 1 by alpha squared will be treated as constant here. So bring it outside. So minus 1 by alpha squared into integral of secant squared of x by 2 is nothing but tan of x by 2 whole divided by 1 by 2. So 1 by 2 and 1 by 2 will get cancelled, and we will be left with tan of x by 2, which is from 0 to pi by 2. So by applying the limits, we will be getting tan of pi by 4 minus tan 0, but tan pi by 4 is 1 and tan 0 is 0. So minus 1 by alpha squared into 1 minus 0, which is nothing but minus 1 by alpha squared. Hence LHS is equal to RHS. That is, d phi by d alpha is equal to integral of a to b dou by dou alpha of f of x comma alpha into dx, which is the Leibniz rule. That is what we verified till now. So we considered LHS and we found LHS value. We considered RHS and we found RHS value, and we proved that those two are equal. Hence Leibniz theorem is verified. And here the limits of the integration are constants. So this is the Leibniz's formula. Now the second problem is verify Leibniz rule of differentiation under integral sign for the integral of 0 to infinity e to the power minus alpha x into cos bx into dx, where alpha is the parameter. And even here, let phi of alpha, as we discussed earlier, if we simplify this, we will get the resultant answer in terms of alpha. That's why let us take phi of alpha is equal to integral of 0 to infinity e to the power minus alpha x into cos bx into dx. Here, by observing the limits, this is 0 and infinity, which are constants. So the Leibniz rule becomes d phi by d alpha is equal to integral of a to b dou by dou alpha of f of x comma alpha into dx. This is the Leibniz rule, and the problem is given as verify. That's why we have to prove LHS is equal to RHS. So first let us find what is LHS value. LHS is d phi by d alpha, that is d by d alpha of this function. So first let us evaluate this integral, which I have done on right side. So phi of alpha is equal to integral of 0 to infinity e to the power minus alpha x into cos bx into dx. And we know that integral of e to the power alpha x into cos bx into dx is equal to e to the power alpha x by alpha squared plus b squared into alpha, that means this coefficient of x, alpha into cos bx, plus the coefficient of x here is b, so b into sin bx it is, which is very important formula which we learn in the lower classes. So apply this formula. This is a straight formula. So in place of alpha we have minus alpha. So if you apply this formula, we will be getting e to the power minus alpha x into alpha x divided by a squared plus b squared into minus alpha cos bx plus b sin bx. The integration is evaluated since this is a formula. Now we have to apply the limits 0 to infinity. Now let us apply the upper limit first. The upper limit is infinity. So e to the power minus infinity it will become, and we know that e to the power minus infinity is 0. So 0 into anything will become 0. So 0. The upper limit becomes 0 minus, let us see the lower limit. The lower limit is 0. So e to the power 0 is 1. 1 divided by alpha squared plus beta squared. So 1 divided by alpha squared plus beta squared into, let us see about this term. So since x is 0, cos 0 is 1. So minus alpha into 1 is minus alpha plus sin 0 is 0. So we will be getting this, minus into minus becomes plus. So alpha divided by alpha squared plus b squared. So phi of alpha is alpha divided by alpha squared plus b squared. So now we are going to substitute this phi of alpha in this LHS, so that it will become d by d alpha of phi. Phi is alpha by alpha squared plus b squared. Now we have to differentiate this function. The differentiation is with respect to alpha, and alpha is there in both numerator as well as in denominator. So we have to apply u by v formula, that is denominator in differentiation of numerator into, that is differentiation of numerator is alpha, differentiation of alpha is 1 into denominator alpha squared plus beta squared for b squared minus numerator into, that is alpha into differentiation of denominator, that is differentiation of alpha squared plus b squared with respect to alpha is 2 alpha. So alpha into 2 alpha by denominator whole square. So alpha squared plus b squared whole square, which on simplification gives minus alpha squared plus b squared divided by alpha squared plus b squared whole square. This is the LHS value. Now let us see what is RHS. RHS of Leibniz rule is integral of a to b dou by dou alpha of f of x comma alpha into dx. So let us do the simplification for this. Here RHS is equal to integral of a to b. Our limits are from 0 to pi by 2 dou by dou alpha of f of x comma alpha. Our function is e to the power minus alpha x into cos bx into dx. Now let us do the differentiation of this. The differentiation will become, here this is in the form of u into v, dou by dou alpha of e to the power minus alpha x into cos bx. We are doing the differentiation with respect to alpha. Alpha is only here, so this is treated as constant. So differentiation of e to the power minus alpha x will become minus x into e to the power minus alpha x, because e to the power minus alpha x into differentiation of minus alpha x with respect to alpha, which is nothing but minus x, which I written here at the beginning, into cos bx I written as it is because there is no alpha in this, into dx. Now the integrand is, that means the step becomes integral of 0 to pi by 2 minus x into e to the power minus alpha x into cos bx into dx. This is the product of three functions under the integral sign. So what we will do here is, since we know the formula of integral of e to the power alpha x into cos bx, which we already discussed, I will apply u into v formula, integral of u into v formula, where u is x and v is e to the power minus alpha x into cos bx. That is what I written here. Since integral of uv into dx is equal to u into integral of v dx minus integral of whatever the term we written here, the same term we will be getting here, integral of v dx into the differentiation of the first function, that is du by dx into dx. Here u is equal to x and v is e to the power minus alpha x into cos bx. Now let us apply these values, that means let us substitute these values in this formula, which gives, that is equal to u into, our u is minus x, so minus x into integral of v dx, that is e to the power minus alpha x into cos bx into dx, minus integral of whatever the function we are having here, that is integral of e to the power minus alpha x into cos bx into dx into differentiation of x into dx. I substituted the values of u and v in this formula, so that we will be getting minus x into integral of this function is, sorry, this integral is not there. Integral of e to the power minus alpha x into cos bx into dx is e to the power minus alpha x by a square, alpha square plus b square into, this is the formula which we already discussed. See, this is the formula, e to the power alpha x into cos bx into dx is equal to e to the power alpha x by alpha square plus b square into alpha cos bx plus b sin bx, that is this coefficient b into sin bx. Similarly, integral of e to the power alpha x into sin bx into dx is equal to e to the power alpha x by alpha square plus b square into alpha sin bx, alpha sin, since it is a sine function, we will be getting alpha sin bx plus the coefficient of x here is b into cos bx. So by applying this formula, here we will get this e to the power minus alpha x by alpha square plus b squared into alpha cos bx plus b sin bx. The limits of integration are from, sorry, the problem is the limits of the integration are from 0 to infinity. So here the limits of integration are 0 to infinity it is. This is infinity, this is also infinity. From here after onwards it is correct. So let us see, from 0 to infinity plus integral of 0 to infinity. Here the second formula is whatever the function we have got here, the same function we have to write here into d by dx of x, that is 1 into dx, that is equal to. Now for this, let us apply the limits. That is upper limit. Upper limit is infinity. So e to the power minus infinity is 0. So 0 into this complete thing will become 0 minus the lower limit is 0, and here we have x. In place of x, if I substitute 0, 0 into anything will become 0. So this complete value becomes 0 plus. Here 1 divided by alpha squared plus b squared is constant because we have to do the integration with respect to x. So 1 by alpha squared plus b squared, bring it out into, here I written this integral of 0 to infinity e to the power minus alpha x separately for this term and for this term, so that alpha, here alpha is there, that alpha I written as it is into integral of 0 to infinity e to the power minus alpha x into cos bx into dx plus, here b is there, so b into integral of 0 to infinity e to the power minus alpha x into sin bx into dx. And here already we discussed the formula, integral of e to the power alpha x into cos bx is e to the power alpha x into alpha x divided by alpha squared plus b squared into alpha cos bx plus b sin bx, and similarly integral of e to the power alpha x into sin bx into dx is equal to e to the power alpha x by alpha squared plus b squared into alpha sin bx plus b cos bx. I substituted these values in this formula, so that means this formula in this, so that we will be getting 1 divided by alpha squared plus b squared. I written this as it is into, here we will be getting e to the power alpha x by alpha squared plus b squared, that is e to the power, in place of alpha x we have minus alpha x, so e to the power minus alpha x by alpha squared plus b squared we will get for this function as well as for this function also. That's why I taken it out at the beginning itself into this alpha I written as it is into, now for this I applied the formula, that is alpha cos bx plus b sin bx. So alpha cos bx plus b sin bx we will get plus b into, here this b I written as it is into alpha sin bx minus b cos bx we will get here from 0 to infinity, which gives, that is equal to 1 by alpha squared plus b squared into e to the power minus alpha x by alpha squared plus b squared into alpha is alpha squared into cos bx plus alpha into b is alpha b sin alpha bx plus b into alpha is b alpha sin bx, plus into minus is minus b squared cos bx from 0 to infinity, so that here alpha b sin bx will get cancelled, and we will be left with, and we have to apply the limits. So if you apply the limits for this, we will be left with here 1 divided by alpha squared plus b squared into alpha squared plus b squared, which is nothing but alpha squared plus b squared whole square into, these two terms gets cancelled, e to the power minus infinity is 0. So the upper limit is 0 minus, let us apply the lower limit. If we apply the lower limit, we will be getting e to the power minus 0 is 1 into alpha squared into cos 0 is 1. So minus alpha squared will be there. Since we are applying lower limit here, we will be getting minus, and this is sin 0 is 0 and sin 0 is 0, and moreover this 0 minus b squared into cos bx. So cos 0 is 1 and minus b squared into 1, but since we are applying lower limit, minus we will get, so minus into minus becomes plus. So minus alpha squared plus b squared, that is equal to minus alpha squared plus b squared divided by alpha squared plus b squared whole squared. sorry, here I said this term gets cancelled. Both are positive, so it won't get cancelled. So that we will be getting RHS as minus alpha squared plus b squared divided by alpha squared plus b squared whole square. So from 2 and 3, that is LHS value is, this is our LHS value, minus alpha squared plus b squared by alpha squared plus b squared whole square, and we have got the RHS as minus alpha squared plus b squared by alpha squared plus b squared whole square. So from these two we can say that LHS is equal to RHS, that is d phi by d alpha is equal to integral of 0 to infinity dou by dou alpha of e to the power minus alpha x into cos bx into dx. Thus, Leibniz rule is verified. Now, let us see the third problem. The third problem is given as verify Leibniz rule of differentiation under integral sign for integral of alpha to alpha squared log of alpha x into dx. Here, by observing this problem, the variables, that means the limits are alpha and alpha squared, which are the parameters. In the previous two problems, whatever we have done, the limits are constants. But here in this problem, the limits are variables. So let us see what is Leibniz rule when the limits are variables. By theorem 1 of Leibniz rule, we have d phi by d alpha is equal to integral of a of alpha to b of alpha. This will become, that means for this we have to do partial differentiation with respect to alpha, that is dou by dou alpha of f of x comma alpha into dx plus d by d alpha of b of alpha into f of b of alpha comma alpha minus d by d alpha of a of alpha into f of a of alpha comma alpha. This is the Leibniz formula when the variables, that means when the integral has variable limits. Here the limits of the integration is alpha and alpha squared, which are variables. That's why we have to apply this formula to evaluate the integration. Now here, by comparing this with the given problem, in place of f we have log of alpha x. So f of x comma alpha is equal to log of alpha x comma the upper limit or the lower limit is alpha, which is nothing but a of alpha is equal to alpha, and the upper limit is alpha squared. So b of alpha is alpha squared. Now the problem is given as verify. So you have to prove LHS is equal to RHS. So first let us evaluate what is LHS, that is d phi by d alpha. But what is our phi? Our phi is nothing but integral of alpha to alpha squared log of alpha x. This is what the given problem is. Evaluate alpha to alpha square log of alpha x. So our phi of alpha is equal to integral of alpha to alpha square log of alpha x. Now let us see how to evaluate this integral. This phi of alpha can be written as alpha to alpha square log of alpha x into dx. This is in the form of log of ab, and we know that log of ab is equal to log a plus log b. So I written this log of alpha x as log of alpha plus log of x into dx from integration alpha to alpha squared. And we are doing integration with respect to x. That's why log alpha is constant, bring it out, and so that we will be left with integral of 1 into dx plus integral of alpha to alpha squared. Here we have log x into dx. So log alpha is written as it is, and we know that integral of 1 is nothing but x. Since we evaluated the integration, the limits are written on right side, alpha to alpha square plus integral of log x. We know that integral of log x is equal to x log x minus x. So in place of integral of log x, I written x log x minus x from alpha to alpha squared. That implies to phi of alpha is equal to, let us apply the limits in place of x, so that we will be getting log of alpha into, in place of x apply upper minus lower limits, alpha squared minus alpha plus For this x log x, apply the upper limit minus lower limit, so that we will be getting upper limit is alpha squared log alpha squared log of alpha squared, minus apply the lower limit, that is alpha. So minus alpha into log alpha, minus of for this x, apply upper as well as the lower limit, so that we will be getting alpha squared minus alpha. So substituting this phi of alpha. So our phi of alpha is this. Now let us substitute this phi of alpha in LHS of the Leibniz rule, that is d phi by d alpha, which gives LHF is equal to d phi by d alpha, that is equal to d by d alpha of phi. Phi is this complete thing. So d by d alpha of log of alpha into alpha squared minus alpha plus alpha squared into log alpha squared into log alpha squared minus alpha log alpha minus of alpha squared minus alpha. Now we have to find the differentiation of this entire function with respect to alpha. Let us see how to find it. Here, log alpha into alpha squared minus alpha. This is in the form of u into v. So, log alpha I written as it is into differentiation, and we know the differentiation of uv, that is u into dv by dx plus v into du by dx, or the otherwise also. So, log alpha I written as it is into differentiation of alpha squared minus alpha. Differentiation of alpha squared is 2 alpha minus differentiation of alpha is 1 plus alpha squared minus alpha I written as it is into differentiation of the first function, that is log alpha. Differentiation of log of alpha is 1 by alpha. So, this is the differentiation of this function plus. For this, let us apply uv formula once again. So, first function alpha squared into differentiation of log of alpha squared is 1 by alpha squared into differentiation of alpha squared is 2 alpha plus log of alpha squared as it is into differentiation of alpha squared is 2 alpha. So, this complete thing is the differentiation of this function. Next, minus differentiation of alpha log alpha into I written as it is, differentiation of log alpha is 1 by alpha plus differentiation of alpha is 1 into different log alpha I written as it is. So, this is the differentiation of this function, minus of differentiation of alpha squared minus alpha. Differentiation of alpha squared is 2 alpha minus differentiation of alpha is 1. So, this is the differentiation of this function. Now, let us do the simplification to this. So that we will get 2 alpha minus 1 into log alpha, I written as it is, plus alpha squared into 1 by alpha is alpha minus alpha into 1 by alpha is 1 plus alpha squared into alpha squared will get cancelled here, so that we will be left with 2 alpha. So 2 alpha written as it is plus 2 alpha into log of alpha squared written as it is minus of alpha into alpha will get cancelled, we will get minus 1 minus of plus is minus log alpha minus 2 alpha minus of minus is plus 1. So, d phi by d alpha is equal to 2 alpha into log alpha minus 1 into log alpha is log alpha plus alpha minus 1 plus here 2 alpha into log alpha squared is, here you see, plus 2 alpha minus 2 alpha will get cancelled, and plus 2 alpha into log alpha squared. We know that log alpha squared is equal to 2 log alpha. Log of a to the power m is m log 2 or m log a. So 2 log alpha. So this can be written as 2 alpha into 2 log alpha, which is nothing but 4 alpha log alpha, and here minus 1 plus 1 will get cancelled, and this minus log alpha written as it is. So, therefore, d phi by d alpha is equal to 6 alpha log alpha minus 2 log alpha plus alpha minus 1. This is our LHS value. Now, let us find RHS. RHS is integral of alpha to alpha squared dou by dou alpha of log of alpha x into dx. That is here sorry, RHS is this one. This is not there. So our RHS is integral of alpha to alpha squared dou by dou alpha of f of x comma alpha into dx plus d by d alpha of, that is, let us see the formula once. Integral of a alpha to b alpha dou by dou alpha of f of x comma alpha into dx plus d by d alpha of the upper limit into f of b of alpha comma alpha minus d by d alpha of the lower limit into f of a alpha comma alpha. This is the RHS of the Leibniz theorem. That's why here RHS will become this one. Integral of alpha to alpha square dou by dou alpha of f of x comma alpha into d alpha plus d by d alpha of the upper limit b of alpha into f of b of alpha comma alpha minus d by d alpha of lower limit a of alpha dot f of a of alpha comma alpha. That is equal to integral of alpha to alpha square f of x comma alpha. Here f of x comma alpha is log of alpha x. That is what our problem is. Comma, the upper limit is alpha squared, which is nothing but b of alpha, and the lower limit is alpha. So that is our a of alpha. So a of alpha is equal to alpha, b of alpha is equal to alpha squared. Now let us substitute these values in this formula, so that we will get dou by dou alpha of f of x comma alpha. F of x comma alpha is log of alpha x. So dou by dou alpha of log of alpha x into dx plus d by d alpha of b of alpha. B of alpha is alpha squared. So d by d alpha of alpha squared into f of b of alpha comma alpha. F of x comma alpha is equal to log of alpha x. I want to find f of b of alpha comma alpha. What is b of alpha? Alpha squared. So f of alpha squared comma alpha, it will become, which is nothing but log of alpha into, in place of x substitute alpha squared, so that it will become log of alpha cube. So that is equal to f of b alpha comma alpha will become log of alpha cube minus d by d alpha of a of alpha. A of alpha is nothing but alpha. So written alpha into f of a of alpha comma alpha. F of a of alpha comma alpha will become what? Log of f of x comma alpha is log of alpha x. So a alpha is nothing but alpha. So log of alpha into alpha, that is log of alpha squared. So f of a of alpha comma alpha is log of alpha squared. That is what I substituted here. Now let us do the simplification to this. That is equal to integral of alpha to alpha squared dou by dou alpha of log of alpha x. Differentiation of log is 1 by alpha x into, we are doing the differentiation with respect to alpha. So treat x as constant, so that we will get 1 by alpha x into differentiation of alpha is 1 into x, we will get as it is into dx plus differentiation of alpha squared is 2 alpha. We are doing the differentiation of only alpha squared. We are not applying UV formula here. So differentiation of alpha squared is 2 alpha into log of alpha cube written as it is minus differentiation of alpha is 1 into log of alpha squared. That is equal to integral of alpha to alpha squared 1 by x, and x will get cancelled. So that we will be getting 1 by alpha into dx plus, there is no change in these two terms. These two terms carried as it is. That is equal to, here we are doing integration with respect to x. So 1 by alpha is constant. Bring it out. Different integration of 1 is x. So apply the limits alpha to alpha squared plus 2 alpha log alpha cube minus log alpha squared. No change in these two terms. So that if you apply the limits to this, we will get 1 by alpha into, apply the upper limit alpha squared minus alpha plus 2 alpha log alpha cube minus log alpha squared. So if you split the brackets here, we will be getting 1 by alpha into alpha squared is alpha, which I written here, minus 1 by alpha into alpha is minus 1. So minus 1. 2 alpha log alpha cube. Log alpha cube is nothing but 3 log alpha. 3 into 2 alpha will become 6 alpha log alpha minus log alpha squared can be written as 2 log alpha by using this formula, so that we will be getting the RHS value as 6 alpha log alpha minus 2 log alpha plus 1 minus 1. Now LHS value also we got the same, 6 alpha log alpha minus 2 log alpha plus alpha minus 1. Even RHS value also we got the same, 6 alpha log alpha minus 2 log alpha plus alpha minus 1. Therefore, from 2 and 3, we can say that d phi by d alpha is equal to this whole thing. Thus, Leibniz theorem is verified. Now, see the next problem. The next problem is, if phi of alpha is equal to integral of alpha to alpha squared cos of alpha x by alpha into dx, where alpha is greater than 0 is a parameter, then find d phi by d alpha by using Leibniz rule of differentiation. So here given phi of alpha is equal to integral of alpha to alpha squared cos of alpha x by alpha into dx. So here f of x comma alpha is cos of alpha x by alpha, and the upper limit is alpha squared, which is nothing but our b of alpha, and the lower limit is alpha, so a of alpha is equal to alpha. The problem is asked as find d phi by d alpha by using Leibniz rule. So here we are not doing the verification, we are finding d phi by d alpha. In all the previous problems, in all the above 3 problems, we verified Leibniz rule. So we considered LHS, we have done simplification, we considered RHS, we have done simplification, and we proved LHS is equal to RHS. But in this problem, it is asked as find d phi by d alpha by using Leibniz rule. So directly I am applying Leibniz rule here. Since the limits of integration are variables by theorem 1 of Leibniz rule, here alpha and alpha squared are variable, limits are variables. So the Leibniz rule will become d phi by d alpha is equal to integral of alpha to alpha squared dou by dou alpha of f of x comma alpha into dx plus d by d alpha of the upper limit into f of b of alpha comma alpha minus d by d alpha of the lower limit into f of lower limit comma alpha. This is the Leibniz formula. So in this formula, I am going to substitute the values now. So let us compare with the given problem. Actually we have to evaluate phi of alpha is equal to this. So our f of x comma alpha is cos of alpha x by alpha. So f of x comma alpha is equal to cos of alpha x by alpha, and the upper limit is alpha squared, which is nothing but b of alpha, and the lower limit is alpha, so a of alpha is equal to alpha. In the formula we are having f of b of alpha comma alpha, so let us find its value. F of x comma alpha is equal to cos of alpha x by alpha. So f of b of alpha, this is alpha squared. So f of alpha squared comma alpha is equal to cos of alpha into alpha squared whole divided by alpha, that is equal to cos of alpha cube by alpha. Similarly, f of a of alpha comma alpha, in the formula we have f of a of alpha comma alpha also. So let us find its value. F of a of alpha comma alpha is equal to f of a of alpha is alpha, alpha comma alpha, that is cos of alpha into, in place of x we have to substitute alpha. So alpha into alpha by alpha, that is equal to cos of alpha squared by alpha. So in this formula, in place of f of a of alpha comma alpha, I will substitute this value, and in place of f of b of alpha comma alpha, I will substitute this value, so that this formula becomes d phi by d alpha is equal to integral of alpha to alpha square dou by dou alpha of f of alpha. F of alpha is nothing but f of alpha is nothing but cos of alpha x by alpha. So dou by dou alpha of f of x comma alpha, that is cos of alpha x by alpha into dx, plus d by d alpha of b of alpha. B of alpha is alpha squared. So d by d alpha of alpha squared into f of b of alpha comma alpha. F of b of alpha comma alpha is cos of alpha cube by alpha. So cos of alpha cube by alpha minus d by d alpha of a of alpha. A of alpha is alpha. So d by d alpha of alpha into f of a of alpha comma alpha. F of a of alpha comma alpha is cos of alpha squared by alpha. So I written this. So that we will get integral of alpha to alpha square. Now let us do the differentiation of this function with respect to alpha, partial differentiation. Here alpha is there in the numerator as well as in the denominator. So let us apply u by v formula, which gives denominator into differentiation of cos of alpha x. Differentiation of cos is minus sine alpha x into differentiation of alpha x is x, because we are doing differentiation with respect to alpha. X is treated as constant here, minus numerator into cos of alpha x into differentiation of denominator. Differentiation of alpha with respect to alpha is 1 whole divided by denominator square, that is alpha square, plus differentiation of alpha squared is 2 alpha into cos of alpha cube by alpha minus differentiation of alpha with respect to alpha is 1 into cos of alpha squared by alpha. That implies to d phi by d alpha is equal to, here we have to do the integration with respect to x. So alpha we can bring it out. We can get alpha is treated as constant here. So alpha to the power minus 2 into integral of alpha to alpha squared. Here dx is missing, minus x alpha into sine alpha x minus cos alpha x into dx. Dx are written here as it is, plus alpha alpha gets cancelled, 2 into cos of alpha cube minus cos of alpha squared by alpha. That implies to d phi by d alpha is equal to, minus is there in both the terms. So bring it out. Minus alpha, sorry, I did not bring it out. I am splitting this integral separately for this term and for the second term, so that it will become minus alpha to the power minus 2 into integral of alpha to alpha square x alpha into sine of alpha x into dx minus alpha to the power minus 2 into integral of the second term, that is cos of alpha x into dx, plus these two terms written as it is. So that minus alpha to the power minus 2 into, here we are doing integration with respect to x. So alpha is treated as constant. So bring it out, so that we will be left with integral of alpha to alpha square x into sine alpha x into dx minus alpha to the power minus 2 into integral of cos of alpha x into dx plus 2 cos alpha cube. That means I written these two terms as it is. Now let us see how to evaluate this integral. This integral we are doing with respect to x. So this is in the this is having product of two functions. So we have to apply u into v formula. We know that integral of uv dx is equal to u into integral of v dx minus integral of v dx into du by dx. Here u is equal to x and v is equal to sine of alpha x, that is equal to u is x. So this integral is not there. By mistake it had come. So let us cancel this. So x into u into means x into integral of v dx, that is integral of v is what, sine of alpha x. So integral of sine of alpha x into dx minus integral of whatever the function we have here, the same function, integral of sine of alpha x into dx into du by dx, means d by dx of x into dx. So d phi by d alpha is equal to this alpha to the power minus 2 into alpha will become alpha to the power minus 1 into integral of x integral of x sin alpha x is x into integral of sin alpha x is minus cos alpha x by alpha plus, because minus into minus will become plus, 1 into differentiation of x is 1 into integral of this alpha x by alpha is nothing but sin of alpha x by alpha squared. Since I evaluated the integration here, I am going to apply the limits alpha to alpha squared minus alpha to the power minus 2 into integral of cos of alpha x is sin of alpha x by alpha, because we are doing integration with respect to x. So alpha is treated as constant by alpha, from alpha to alpha square, plus written these two terms as it is, no change. That implies to d phi by d alpha is equal to this minus alpha to the power minus 1 I written as minus 1 by alpha into minus 1 by alpha into this x into cos alpha x I written in brackets plus 1 by alpha squared into sin alpha x from alpha to alpha squared minus this alpha is there in the denominator, take it to the numerator so that it will become alpha to the power minus 3 into, for this sin alpha x, apply the upper as well as the lower limits, plus no change in these two terms I carried as it is. That applies to d phi by d alpha is equal to minus 1 by alpha into, now for this term apply the upper as well as the lower limits in place of x. So minus 1 by alpha into upper limit is alpha squared, substitute in place of x, so that it will become alpha squared into cos of alpha into alpha squared, which is nothing but alpha cube, minus lower limit is alpha, so alpha into cos of alpha into alpha squared. Next, minus into plus is minus 1 by alpha into 1 by alpha squared is 1 by alpha cube into, for this sin alpha x, apply upper as well as the lower limit, so that we will be getting sin alpha cube minus sin alpha squared minus alpha to the power minus 3 can be written as 1 by alpha cube into, apply the upper limit so that it will become sin alpha cube minus sin alpha squared plus no change in these last two terms, write it as it is. That applies to d phi by d alpha is equal to, let us do simplification to this, minus 1 by alpha into minus 1 by alpha is 1 by alpha squared into cos of alpha cube, and then we are having minus 1 by alpha minus 1 by alpha into minus 1 by alpha is minus 1 by alpha squared into minus. So minus 1 by alpha squared into cos alpha squared minus 1 by alpha cube into sin alpha cube and minus 1 by alpha cube into sin alpha squared minus 1 by alpha cube into sin alpha cube, minus into minus becomes plus 1 by alpha cube into sin alpha squared plus 2 cos alpha cube minus cos of alpha squared by alpha. Now let us do still simplification to this. Alpha squared will get cancelled, and by doing the simplification to this we will get d phi by d alpha is equal to 3 cos alpha cube minus 2 into cos of alpha squared by alpha minus 2 sin alpha cube by alpha cube plus 2 into sin of alpha squared by alpha cube. By taking LCM we will get alpha cube, so that 3 alpha cube cos alpha cube minus 2 alpha squared, alpha cube is LCM, so 2 alpha squared cos of alpha squared minus 2 sin alpha cube plus 2 sin alpha squared. This is our d phi by d alpha. Here, therefore, by Leibniz theorem, d phi by d alpha is equal to this one. That is, here we have not done the verification. The problem is asked as find d phi by d alpha by Leibniz rule. That's why by applying Leibniz rule, we found what is d by d alpha of cos of alpha divided by alpha. This is the final answer. Now, let us see the next problem, which is very important for the examination point of view. The next problem is evaluate integral of 0 to alpha log of 1 plus alpha x by 1 plus x squared into dx. Hence prove that integral of 0 to 1 log of 1 plus x by 1 plus x squared into dx is equal to pi by 8 into log 2. Here the problem is integral of 0 to alpha log of 1 plus alpha x by 1 plus x squared into dx. Nothing is given, like apply Leibniz rule. To evaluate this integral, without applying Leibniz rule, we can't evaluate this by applying any of the known methods whatever we learned till now, because here we are having x in the numerator as well as in the denominator, and we have to evaluate the integration of this. So there is no other option, we have to apply Leibniz rule. So for that sake, we have taken let phi of alpha is equal to integral of 0 to alpha log of 1 plus alpha x by 1 plus x squared into dx. Here, by comparing this with Leibniz rule, f of x comma alpha is equal to log of 1 plus alpha x by 1 plus x squared, comma a of alpha, lower limit is 0 and b of alpha is alpha. Next, phi of alpha is equal to this. Since the limits of integration are variables, because b of alpha is alpha, by Leibniz rule, we will get d phi by d alpha is equal to integral of 0 to alpha dou by dou alpha of the given function f of x comma alpha into dx plus d by d alpha of the upper limit into f of b of alpha comma alpha minus d by d alpha of the lower limit into f of a of alpha comma alpha. Now let us find what is f of b of alpha comma alpha and f of a of alpha comma alpha. Given f of x comma alpha is equal to log of 1 plus ax by 1 plus x squared, that is equal to, but here f of b of alpha comma alpha is b of alpha is alpha. So log of 1 plus, in place of x substitute alpha, so that alpha into alpha divided by 1 plus alpha squared, that is equal to log of 1 plus alpha squared by 1 plus alpha squared. Next, f of a of alpha. Here a of alpha is 0. So log of 1 plus alpha into 0 divided by 1 plus 0, which is nothing but log 1, but we know that log 1 is 0. That's why f of a of alpha comma alpha will become 0. By substituting these two values in this formula, we get d phi by d alpha is equal to integral of 0 to alpha dou by dou alpha of f of x comma alpha, that is log of 1 plus alpha x by 1 plus x squared into dx plus d by d alpha of b of alpha. B of alpha is alpha. So into f of b of alpha comma alpha. F of b of alpha comma alpha is log of 1 plus alpha squared by 1 plus alpha squared minus 0. That implies to d phi by d alpha is equal to integral of 0 to alpha dou by dou alpha of log of 1 plus alpha x by 1 plus x squared into dx. 1 plus x squared is constant, so write it as it is, into differentiation of log of 1 plus alpha x with respect to alpha, because we are doing partial differentiation here. So x is treated as constant. Differentiation of log is 1 divided by 1 plus alpha x into differentiation of alpha x is x. So that this will become integral of 0 to alpha x divided by 1 plus alpha x into 1 plus x squared into dx plus differentiation of alpha is 1 into log of 1 plus alpha squared by 1 plus alpha squared. Now we have to evaluate this integral. It is not so easy to evaluate this integral because integration we are doing with respect to x. X is there in the numerator and in the denominator we have product of two functions. So we can evaluate this type of integral by using partial fractions, which we learned in second PU. So let x divided by this, let us resolve this integrand into partial fractions first. The integrand is, so first I am considering the integrand, that is x divided by 1 plus alpha x into 1 plus x squared, that is equal to, since 1 plus alpha x is a linear factor, I will be taking the general form as a divided by 1 plus alpha x plus this 1 plus x squared is a quadratic factor. For this, the partial fraction is bx plus c divided by 1 plus x squared. So by taking LCM and by cancelling the denominators, we will get x is equal to a into this denominator 1 plus x squared plus bx plus c into this denominator, that is 1 plus alpha x. Now we will be finding the values of a, b and c by putting x is equal to minus 1 by alpha. We get a is equal to this much, and next we equated the corresponding coefficients of x squared, so that we got b is equal to this much, and next we substituted x is equal to 0, so that we got c is equal to this much. Now substitute ABC values in equation number 3, which gives x divided by 1 plus alpha x into 1 plus x squared is equal to minus alpha by 1 plus alpha x into 1 plus alpha squared plus x plus alpha divided by 1 plus alpha squared into 1 plus x squared. But we actually have to find integral of this function. Till now we resolved this into partial fractions to reduce it to the standard form of integration. So now let us integrate on both the sides so that the above step becomes integral of x divided by 1 plus alpha x into 1 plus x squared into dx is equal to integral of 0 to alpha this complete term into dx, that is equal to, here we are doing integration with respect to x. So this alpha by 1 plus alpha squared is treated as constant. So this 1 plus alpha squared, I brought it outside. So minus 1 by 1 plus alpha squared into integral of 0 to alpha. We will be left with alpha divided by 1 plus alpha x into dx. And I'll tell you why I written this alpha inside the integral. Plus 1 by alpha squared is constant, write it outside, and here we are having sum of two terms in the numerator. So write down this integral separately for both the terms, so that it will become integral of 0 to alpha x divided by 1 plus x squared into dx plus alpha by 1 plus alpha squared into integral of 0 to alpha 1 by 1 plus x squared into dx, that is equal to minus 1 by 1 plus alpha squared into integration of this alpha by 1 plus alpha x into dx is log of the denominator, because we are having one standard formula, that is integral of f dash of x by f of x into dx is equal to log of f of x. That is, if the function is there in the denominator and if its differentiation is there in the numerator, we can write it as log of f of x. So this integral will become a log of the denominator, that is log of 1 plus alpha x. Since we applied the integration, limits I written it on the right side, 0 to alpha plus 1 by 1 plus alpha squared into integral of this. Again, the differentiation of the denominator is 2x, but in the numerator we have only x. So to get 2x, multiply and divide with half, means 2. So 1 by 2 is extra into this integral. We can write it as log of the denominator, that is log of 1 plus x squared from 0 to alpha plus alpha by 1 plus alpha squared into integral of 1 by 1 plus x squared is tan inverse x from 0 to alpha, that is equal to minus 1 by 1 plus alpha squared into log of 1 plus alpha squared by applying the upper as well as the lower limits, plus 1 by 1 plus alpha squared into this also the same case, and apply the upper as well as the lower limit. Therefore, integral value is this. Substituting this in equation number 2, we will get d phi by d alpha is equal to minus in log of 1 plus alpha squared by 2 into 1 plus alpha squared plus alpha, that means whatever we have here I written, plus the second term. Equation number 2 is this is our equation number 2. In this equation number 2, till now we found the value of this integral of 0 to alpha, this value we have done till now. So that value I substituted plus this log of 1 plus alpha squared by 1 plus alpha squared I written here. So d phi by d alpha is equal to log of 1 plus alpha squared by 2 into 1 plus alpha squared plus alpha by 1 plus alpha squared into tan inverse alpha. Because here this term and this term are the same, but this is minus half, this is plus 1. So we will be getting plus half. So plus half of log of 1 plus alpha squared by this. But the problem is given as find phi of alpha. Otherwise, evaluate. The problem is given as evaluate integral of this. We have taken integral of this as phi of alpha. So we have to find phi of alpha. But till now, whatever we have done, it is to find d phi by d alpha. So d phi by d alpha is this much we got. But we have to find phi of alpha. So to find phi of alpha, integrate this d phi by d alpha on both the sides, which gives phi of alpha. So phi of alpha is equal to integral of this right hand side with respect to alpha. So 1 by 2 into integral of log of 1 plus alpha squared by 1 plus alpha squared plus integral of alpha by 1 plus alpha squared into tan inverse of alpha. Now let us see how to evaluate this integral. This is quite lengthy problem. So that is equal to, once again here you see 1 by 2 into integral of log of 1 plus alpha squared by 1 plus alpha squared into d alpha. It is difficult to evaluate because alpha is there in both numerator as well as in the denominator. That's why I did not touch this term. I written this term as it is. There is no change in the first term. I carried it as it is plus integral of alpha by 1 plus alpha squared into tan inverse alpha. This is in the form of u into v. And we know the formula for integral of uv, that is equal to u into integral of v dx minus integral of v dx into du by dx into dx. Here u is tan inverse alpha, v is alpha by 1 plus alpha squared. So by substituting the values, we will get tan inverse alpha into integral of alpha by 1 plus alpha squared is 1 by 2 into log of 1 plus alpha squared by applying f dash of x divided by f of x formula minus integral of this half into log of 1 plus alpha squared into differentiation of tan inverse alpha. Differentiation of tan inverse alpha is 1 by 1 plus alpha squared into d alpha. That implies to phi of alpha is equal to half into integral of log of 1 plus alpha squared by 1 plus alpha squared into d alpha plus half into tan inverse alpha into log of 1 plus alpha squared minus half into log of 1 plus alpha squared by 1 plus alpha squared into dx. You look at this. This is plus half and this is minus half into same terms gets cancelled. Sorry, this is alpha. This is alpha, so that this term and this term will get cancelled. We will be getting therefore integral of 0 to alpha log of 1 plus alpha x by 1 plus x squared into dx is equal to 1 by 2 into tan inverse alpha into log of 1 plus alpha squared. Now let us find, the problem is asked as, and hence prove that integral of 0 to 1 log of 1 plus x divided by 1 plus x squared into dx is equal to this. So by observing the given problem, this is 0 to alpha, this is 0 to 1, log of 1 plus alpha x, log of 1 plus x. That is, in this problem, if you put alpha is equal to 1, we will get this. So here in the final answer, this is the final answer that we have got. In this final answer, I'll substitute alpha is equal to 1 in this, so that we will get integral of 0 to 1 log of 1 plus x divided by 1 plus x squared into dx is equal to 1 by 2 into tan inverse 1. Tan inverse 1 is nothing but pi by 4. Tan of pi by 4 is 1. So 1 into log 1 plus 1, that is equal to log 2. So that is equal to pi by 8 into log 2. Hence, integral of 0 to 1 log of 1 plus x by 1 plus x squared into dx is equal to pi by 8 into log 2, and the references are, okay, thank you. The references are the same references as of the previous session. Thank you.